Hi students. So today in this session we are going to discuss the cyclic annealing, the heat treatment process to improve the material property. So what is this cyclic annealing and why it is adopted? We will discuss all these salient features in this session. Now let me discuss what is the cyclic annealing process and why this is adopted here. Now, let me discuss like this. What is I will start how the cyclic annealing process is done and what is this cyclic annealing process. First of all, what is exactly the cyclic annealing process? That means in any heat treatment process, the first important point is up to what temperature it is going to be heated and in what environment it has to be cooled. Now, at what temperature? That means the temperature range. So, the material that you have taken, it must be heated above the upper critical point. That is very, very important. You have to heat until it reaches above the upper critical point, and the cooling is rapidly predetermined level. So whatever the process, whatever the level that you have taken already, that you have considered already, so you have to cool up to that level immediately. That means the cooling is rapidly, and after that you have to hold for a particular time and then cool to the room temperature. So this is the process that we are adopting. So that means the first step is you have to heat until it reaches above the upper critical point, then cool rapidly to the predetermined level and hold for a particular time, and after that cool to the room temperature. So this is the process that we are adopting in cyclic annealing process to improve the properties. That means this heat treatment process, the main intention. So all these things we are going to discuss in this cyclic annealing session. Now, so you can observe here, this is the iron carbon diagram in which you can observe this is the lower critical point here, and this is the upper critical region. So that means this is the upper critical temperature range. Suppose if you take this, say these are the LIs. For these LIs, this is the upper critical temperature line. And for these LIs, that means for these range up to 2% carbon from 0.83% to 2% carbon steels here, this is the range, this is the upper critical temperature line. So that means you have to heat until it reaches this region just above upper critical temperature line. So it varies from one point to, that is one alloy to another alloy. Suppose if you take 0.83, so this is around 1333 degree Fahrenheit. So this is the temperature range for 0.83 steel. Suppose if you take immediately, so then it may increases to 1400, etc. etc. That means from point to point, from alloy to alloy, the temperature varies, and the upper critical temperature line also, the range also varies from steel to steel. After heated up to this temperature, then you have to cool in this region here. So that means predetermined level and hold it for a second and for a particular time, and after that cool to the room temperature. So this is the procedure that we are adopting in cyclic annealing process. So that means if you compare, cyclic annealing process is a rapid cycle compared to the other process. So if you take the normalizing, so this is the main process, that is the main heat treatment process that we are utilizing for parts that will be hardened and tempered. If you take the other annealing process, that is the other heat treatment process. If you take the annealing process, which refines the grain size and improves the metal toughness. So here, even in normalizing or annealing process, we cannot get the both the properties. But in cyclic annealing, we will get the lot of property changes which we are adopting by normalizing or annealing process. That is the main advantages. That's why we have adopted cyclic annealing process. And you can observe the process here, the timing process here. Here, the main advantage of cyclic annealing process, and whatever the image that you are seeing here, you can see here these lines. You are seeing two lines here, two inclined lines. So this line is for heating line, and this line is for cooling line here. So that means this is the heating rate and this is the cooling rate. So in between heating rate and the cooling rate, if you observe the holding time, so this is a holding time here. So up to what time, that means it is a for a particular, that means uniform maintenance you are going to see here for all the cycles. Cyclic means whatever the time, see here, repeated temperatures. That means you have to heat up to it reaches the above upper critical temperature line. You have to cool it. Rapid cooling is required to the predetermined level, and after that again heating and again cooling. So like this. So that means continuously you have to heat and cool for a particular period of time. So that means here the number, how many number of times that you are heating and cooling. So that you have to be calculated, and with the help of some formulas, cycle number, you could say that if you consider the cycle number as C, holding time as T. So if you multiply this cycle number and holding time, so totally it is a 180 seconds. So that means how many number of cycles, up to what time you have to do. So that means one cycle you have to consider like this. So that means here up from starting to end, how many number of times you have to heat and cool. So that means here the rapid cooling is the main point compared to the other heat treatment process. That means if you consider the normalizing process, or if you consider the annealing process, here the main procedure, or we can say that the main technique that we are adopting in cyclic annealing is the rapid cooling. So due to that, a lot of changes observed in the microstructure or the material properties. Now let us see some more features here. So here this and one more point I want to mention, the cyclic process, whatever the cyclic annealing process that we are saying, that is the heat treatment process, is also considered as isothermal annealing process. That means here, whatever the, when we are adapting heat, the temperature is constant here. So that's why we are saying that it is an isothermal annealing process. And this isothermal annealing process is adapted. That means when this is adapted, and on what materials that we are adopting this cyclic annealing process. So that point is very, very important to do this cyclic annealing process. So here, if you take hypoeutectide, so that means hypoeutectide low carbon steels, that means for these steels you can adopt this cyclic annealing process, and medium carbon structured steels. For these also you can adopt this isothermal or cyclic annealing process, or often. So that means in general we are adopting whatever the cyclic process that we are saying here, that is this heat treatment can be adapted to hypoeutectoid low carbon steels or medium carbon structure steels. For these isothermally, that means cyclic annealing can be adopted. So here after this cyclic annealing process is adopted, the main observation is the machinability. So that means the machinability capability, the main property, the material, whatever the material that we have taken. So after this process is completed, that means after cyclic process is completed, the machinability characteristics increases. That means that it is able to machine. The material is able to machine. The increase, that is very, very important for any material. If the machinability increases, we can do lot of say process on the particular material. That means on the surface especially. Now here after this isothermally, so that means we can say that isothermally annealed structure, that is after heat treatment is completed, the characteristics, what are the characteristics that are going to change is the main advantage is high proportion of ferrite that we are going to adapt. This is the main advantage after this cyclic treatment, that is cyclic annealing heat treatment is completed, and uniformly distributed payload grains. This is also very, very important. So that means if the payload grains are uniformly distributed in a particular material, that is it may be steel or cast iron, automatically we can say that the material will give the important properties that required for machining or any other process. That means for molding, ductility is required. If you want to give the ductility, payload is the main microstructure that we can see in any material. So here it is uniformly distributed. We will get uniformly distributed payload grains because of cyclic annealing process, and fine, very fine lamellar, that means layer by layer perlite grains we can adapt with this cyclic annealing process. And you can see this the uniformly, that means uniaxial. So that means in a particular direction we are going to bread the perlite structures here. You can observe here, this is the cementite in between the ferrite, whatever the gap that you are seeing here in this image. So this is a cementite, hard structure, and this is alpha ferrite structure here. And this region, this is the white region, if you consider this as a austenite region. Compared to ferrite, austenite is a little bit harder. Compared to austenite, cementite is a little bit harder. So that means here the austenite percentage or the ferrite percentage is more. The material can be said as a soft material. That is the main advantage, and it will grow in a uniform direction. So that's why we are saying that after this heat treatment is completed, after this cyclic heat treatment is completed, the perlite is going to form in a uniformly direction and uniformly distributed. And what is this process exactly? We can say in brief, if you want to say in brief of a cyclic annealing process, if you take the steel, whatever the material that you have taken, this is a process where the steel is heated above the upper critical temperature that we are saying up to now. And because of this heating, whatever the heating procedure that we are adopting up to upper critical temperature line, if you heat the material, the structure of the steel, whatever the structure that we have taken here, that is the steel, if you observe before cyclic annealing process and after annealing process, it will be converted rapidly into austenitic structure. This is the main change that we can observe in the material of the steel. So that means after cyclic process or after cyclic annealing heat treatment is completed, we can observe the microstructure that is rapidly converted austenite structures. That means whatever the structure that you have seen previously before cyclic annealing process, it converted rapidly. And the temperature that we have seen here, the steel, whatever the steel that we have taken, so here it has to be cooled to a temperature below the lower critical temperature after heating is completed. That is about 600 to, so that is a below lower critical temperature 600 to 700 degrees centigrade. So this is the temperature range you can see here. This is the upper critical temperature range, and this is the 600 to 700. This is the range we can heat. That is below, this is the lower critical temperature line. So cooling has to be done at this temperature. That means a rapid cooling is adopted. After heating is done up to this temperature, you have to cool rapidly. That is the main technique that we are adopting in cyclic annealing process. And you can observe in another temperature versus time. So this is the austenitic, that is followed by fast cooling to the temperature range of perlitic formation. This is the another image which shows this the heating is adopted above the upper critical temperature line. So this straight line shows the heating and hold for a particular time. So this is the holding time. After that, rapid cooling to the lower critical temperature lines, that is around 600 or 650 degrees centigrade, and again hold it for a particular period. So this is called as a rapid cooling. And after that, it has to be cooled to the room temperature. You can observe the graph between temperature versus time, how much time it has taken at the temperature. And if you observe here, there is no time between holding, after holding at that particular temperature. So that means immediate cooling is required here. And after that, after it reaches to 650 degrees centigrade, again you have to hold for a particular period of time. So it has to be calculated with the formula. Around the total time is around 180 seconds. And after that, you can see here, this is not the rapid cooling. You can take some time here. This is a slow cooling to the room temperature. But here only, if you observe, this is the rapid cooling time here. Okay. That's why austenitic change, whatever the austenitic change we can observe, here you can observe the austenitic change here. and see the complete pay light. So that means whatever the transformation that we are seeing and that we are adopting here to form the complete transformation of peer light here. So that's why after it reaches to cooling, that is to the room temperature, we can observe a clear formation of peer light. And that is the main principle. You can observe in another say process, that is another image here. This is also called as isothermal annealing process. The main intention, the main principle we can say in cyclic annealing is Barnett formation can be avoided only by very slow continuous cooling. But with such a slow cooling, the textured structure results. So that's why we are adopting the another procedure, that is the rapid cooling here. Suppose if you adopt, say, very slow cooling process, the bainite and the other formations can be formed. So we can avoid bainite formation can be avoided. And here, by adopting very, very slow continuous cooling. So that means cyclic cooling we are adopting, rapid and again slow, rapid and again slow. So this is the process that we are adopting in cyclic annealing process. And these are the salient features of cyclic annealing process. So I hope you have understood. In next coming videos, we will discuss a lot of other points in material technology. Thank you one and all.